During this session under quality by experimental design, I will be discussing the 2 to the power k factorial experiment. We have already discussed the factorial experiment in the previous lecture session, and 2 to the power k factorial experiment, if you know in detail, you will have the different kinds of insights about the design of experiment. This is widely used, particularly 2 to the power k factorial experiment. And along with this factorial experiment, you also must be aware of, you must also know what is a fractional factorial experiment. This experiment is also widely used. So these are the two topics I am going to discuss during this session. Now, before I elaborate on this 2 to the power k factorial experiment as well as the fractional factorial experiments, let me highlight or let me explain one important concept that is referred to as the concept of contrast. Is it okay? Like say, what we say that later on when we study the Taguchi method, you will find that the Taguchi method is based on design of experiments, and a particular design he has proposed, that is orthogonal array. An orthogonal array is essentially a one type of fractional factorial experiment, and we come across the term called, say, orthogonal, say the contrast and all. So the basic, what is a contrast, you also must know. So first let me explain what is a contrast, and then I will start explaining what is 2 to the power k factorial experiment. If there are p number of treatments, you know what is a treatment. There can be p minus 1 number of contrast forms that are statistically independent of one another. Is it okay? So out of p number of treatments, you can form p minus 1 number of contrasts. Two contrasts, say L1 and L2, are independent if they are orthogonal to each other. Now, what is this orthogonality that we must first explain, we must define. Suppose the following two contrasts are formed with p number of treatment means. So this could be a linear combination, like L1 is one contrast with this K11 mu1, K12 mu2 plus, and then you go up to the kth level or the pth level, that is K1p into mu p. Is it okay? And similarly, the next contrast you form, that is you have K21 mu1 plus K22 mu2 plus up to the pth level, that is K2p into mu p. So L1 and L2, these two contrasts are formed. The contrast L1 and L2 are orthogonal if and only if, okay, that is you start multiplying these two coefficient values. Is it okay? Like K11 into K21, K12, K22, like this, if you proceed. And ultimately, for all the p treatments you consider, that means summation j equals to 1 to p kij into k2j must be 0. Is it okay? So that is the condition for orthogonality. This means that the sum of the products of the corresponding coefficients, these are the coefficients you have, corresponding coefficients associated with the treatment means, these are the treatment means mu1, mu2, mu p, is 0. Is it okay? So we know what is a contrast. There could be several contrasts, and between two contrasts there could be orthogonality, and we have defined what do you mean by say the orthogonal contrasts. Okay, so this is the basic knowledge or the basic understanding of contrast. Now let me explain what is this 2 to the power k factorial experiment. Now here 2 to the power k means essentially at this first instance you must know that the k means the k number of factors that you are considering in experimentations. Then what is 2? 2 means for each of all these k number of factors you just consider 2 levels. Is it okay? So it is essentially is a k number of factors and each factor at 2 levels. Supposing each factor you consider k number of factors and each factor is at 3 levels, then what could be how do you specify the factorial experiment? It should be 3 to the power k factorial experiment. Is clear? Now, a planned experimentation requires a number of steps to be followed. Is it okay? We have some of the important points we have already explained, like when we started our discussions on design of experiments. So how to carry out the experiment, what is the purpose of experimentation, all these points we have elaborated. So while you conduct an experiment, certain steps you have to follow. So what are those steps? First, the set of factors affecting the response variable. Or the response variables. That means either you consider one important the response variable, or there could be cases where you need to consider a number of response variables simultaneously. So first I must know that what are the factors that are affecting the response variables, and these factors you must first identify. That is the first step. The next step is, on their identification, desirable levels of the selected factors should be known in the second stage. That means now you consider each factor identified and you specify their possible levels. Now these levels can be defined subjectively or it can be defined objectively. Is it okay? And it is better that in order to simplify the experimentation at the initial stage, what you try to do, you start with less number of levels. Okay, so the 2 is the minimum number of levels in most of the experiments. So you start with 2 number of levels for each factor. Finally, it may be of interest to find the relationship between the factor levels, the corresponding responses, and the physical and the economic constants that may have to be considered. So many a time what you need to do, that means even if you know that not only the 2 number of factors or 3 number of factors are affecting y, there could be many other factors might be affecting say the response variable. But the initial stage, you go for simplification. That means you go for experimentations, and while you carry out the experiment, you should consider those factors which are considered to be significant initially. So you need to the screening them. That means even if there are say n number of factors, so you consider just 2 or 3 factors out of n. Okay, and there is a basis for selecting a few number of factors out of many. Okay, so in most cases, in order to represent the reality, the multi-factor experiments are usually employed. Among the multi-factor designs, 2 to the power k factorial experiment is widely used. That means here, as such, we are not restricting the number of the factors, but here in the 2 to the power k factorial experiment, we are restricting the number of levels. Is it okay? So in this 2 to the power k factorial experiment, there are k number of factors, each factor at 2 desirable levels. The total number of treatment combinations is 2 to the power k. For example, if there are 3 factors, each at 2 levels, there are 2 to the power 3 or 8 treatment combinations in each replication. I think it is clear. Usually the level of each factor is thought of as either low or high, like in the previous examples in the earlier the discussion, earlier lecture sessions. We have assumed that the factor A is having low level or high level. So the levels could be either low or high. A treatment is represented by a series of lowercase letters. Okay, like say if the factor is a, we'll be using the small a, or corresponding to capital B factor or capital C factors, we'll be using the small b or the small c. So the lowercase letters we'll be using. The presence of a particular letter indicates that the corresponding factor is at the high level. That means suppose you consider three factors a, b and c. If you use say one combination as small a, it means that the factor a is at the high level, whereas the factor b as well as the factor c, they are at the low level. Okay. So the absence of this letter indicates that the factor is at the low level. So this point you just keep in mind while you write the notations for a particular the combinations. Notation 1 is used to indicate the treatment for which all factors are at the low level. Suppose you are considering the three factors a, b and c, and all these factors, they are having two levels, low level and high level. So the low level is low level, suppose all these three factors, they are at low levels. So how do you specify? You specify at 1. That means 1 in parenthesis. It means that I am considering one treatment combinations where all the three factors are at low level. In many instances, the low level signifies the absence of a factor and the high level its presence. Is it okay? Now here is an example. Suppose there are three factors a, b and c, capital A, capital B and capital C, each at two levels. The set of treatments for this experiment is as follows. That means this is 1 means within parenthesis, it means that all the three factors are at low levels. A means factor A is at the high level, whereas factor B and C at low level. If it is B, that means factor B is at a high level, whereas the factor A and factor C, these are at low levels. AB means basically high level, B at high level. Okay, and this is one say the interaction. Then you consider the C, and AC means another combination, BC is another interaction, and ABC is another combination. Are you getting my point? So that means AB, that means the C is at the low level. Is it okay? If you say C means A and B are at the low levels, where the C is at high levels. So these are the 8 combinations you have in each replication. So I am sure that you have understood the meaning of these notations. Okay. Now if you refer to this figure 1, I'll show you figure 1. Figure 1 shows the layout of a 2 to the power 3 experiment. That means there are 3 factors, each factor at 2 levels, with the factors denoted as A, B and C. In this layout, high levels of the factors are denoted by +1 and the low levels by -1. Is it okay? To estimate the main effects of the factors and the interaction effects between the factors, these are the 2 important considerations you have. The concept of contrast is used. It's clear? So already we have defined what is a contrast. For example, to determine the main effect of factor B, the average values of the observations for which B is at the high level is computed. Okay, so that means out of all the combinations, you select those combinations where the factor B is at the high level, and subtract from this value the average of the observations for which B at the low level. I think it is made very, very clear. So if you want to estimate the main effect of factor B, so this is the rule we follow, and the same rule you have to follow when you compute let's say the main effect of A or other factors, or C, like this. So if there are R replications for each treatment, okay, the main effect of factor B is given by this one. Is it okay? That means here what you find that these are the combinations where B is at the high level. So B at the high level, here also B at the high level, B is at the high level, here also B at the high level, divided by, there are this average value we consider, so divided by 4, and how many such values you have? That means there are replications. That means you have R such R everywhere, you have R number of values of B, R number of values are AB, and so on. So that's why it is divided by 4 into R. And similarly here you will find that the B is at the low level, B at the low level, B, the way we have defined the notation, when you write C, that means B at the low level. When you write AC, okay, the interaction, so you find that B at the low level divided by 4 into R. So this is the ultimate, the simplified expressions for capital B. In equation 1, that means this equation, the lowercase letters denote the sum of the responses for the corresponding treatments. The main effects of each factors can be similarly computed. That means we have just shown calculation for the factor B, but the similar sort of the computations you have for the other two factors, namely factor A and factor C in this case. So this is the pictorial representation of say the 2 to the power k factorial experiment. So if you look at this figure, what you find, you can identify the factor A, factor B, and the factor C, okay, and then what are the combinations. So how many treatment combinations for each replications? So this is at the low level, all three at the low level, here the C at the high level, whereas the factor A and factor B, these are at the low levels, okay. So these are the low levels you have. So just you follow these the corners, you can get an idea that how it is designed and how, on what basis, what is the basis of selecting the treatment combinations, and what is the basis of say the giving notation so for each treatment combinations, okay. Now here is an example. So in order to develop a good quality synthetic fuel, experiments are conducted with 3 different factors, each controlled at 2 levels. So you must have a controlling means, okay. It's not that you get all these values or all these levels automatically. So while you set the values, while you select those levels, you also must be aware of how to control them. Factor A is a concentration of corn extract at 5% and 10%, okay. Factor B is a concentration of another compound at 15% and 25%. And factor C is the distillation temperature at 120 degrees Celsius and 150 degrees Celsius. Is it okay? The degree of undesirable emission level at each treatment combination is shown in table 1 for 3 replication. That means what is your main objective? That means you try to design, okay, the fuel, the synthetic fuel in such a way that the undesirable emission level is at the lowest or the minimum level. Is it okay? So that is your objective, okay. And if you achieve this objective, you say that the quality goal has been achieved. Now for such a problem, you have to adopt, you have to use the design of experiment methodology. Now here, what are the questions we have? There are 3 questions we have. Find the main and the interaction effects. This sort of the questions always you get in any design of experiment exercises. Find the sum of squares for each of the main and the interaction effect. That means essentially you propose a model. That means how the response variable is related to the individual factors, and what is whether the best possible model you are prescribing, and whether all the important or the critical factors you have considered while you model Y or while you carry out the experiment. So these two values you compute and get an idea. That means you need to create the ANOVA table. At 5% level of significance, which effects are significant? So these are the three questions we have. So what are the data you got? That means you have gone for an experiment, and all these 8 treatment combinations with 3 factors at 2 levels you have considered, and there are 3 replications. That means each treatment combination the experiment is run for each treatment combinations 3 times. That's why the replication, there are 3 replications, and you will find that against these treatment combinations, when all these 3 factors are at low levels, you will find that the emission level, the first time when you do the experiment, you get a value of 30, the next time it is 24, and the third time it is 26. And similarly, for all other treatment combinations, you get the data the 3 times. So the 3 times you have to carry out the tests, okay, in a particular condition or in a particular treatment combination. So these are the values for replication 1, replication 2, and replication 3. So look at these values. So this is the data you have collected. Next, what you have to respond to the question number 1. So how to get the solution? In this case, a 2 to the power 3 factorial experiment is conducted, and the number of treatment combinations is 8 for each replication. This we have already elaborated. So you calculate the main effect. Okay, already we have explained that which formula you need to use. Okay. So the main effect of A you compute as 1.083. The other main effects and the interaction effects are calculated in the same manner. We have already given you the formulations. So apply those formulations, and then you create the ANOVA table like this. That means the sources of variation in Y could be A, could be B, could be C, could be AB, AC, BC, ABC. Or the sources of variation you are unable to explain. That means this is the error component, and this is the total say you consider. That means all aspects you have considered. Now you have to check if the error part is insignificant or not. If it is insignificant, you may conclude that your modeling is perfect. If you find that the error is significant, that means immediately you conclude that the model is not perfect. That means you have to make it perfect. Maybe you need to consider some other factors that you have not considered yet. So that's why it is always any such experiment when you conduct, this is referred to as an exploratory study. You never know that whether the factors we are considering, whether those factors are all significant or not, or whether you need to consider some other factors in explaining the behavior of Y, or say the variations in Y. Is it okay? So that's why it is always referred to as an exploratory study. So these are the effects you consider, main effects. The degree of freedom you consider, this the total is 23, and the sum of squares you calculate. Mean square you consider. That means once you consider the degrees of freedom, sum of squares already you have computed. So now you can calculate the mean square, right? And then the F statistic you consider. Is it okay? And then what you conclude, that the sum of squares for factor A is computed like this. Already have given you the steps. You have all the data. The sum of squares for all other main and interaction effects are calculated and shown in the ANOVA table. So just you refer to the ANOVA table, you will get all the details. The total sum of squares is computed with this formula. That means SST, you follow this formula. These values you get from the table, and this is the factor K, correction factor. And at 5% level of significance, this is the value of F statistics, 5% level of significance, and these are the degrees of freedom. It is from the table value is 4.4967. Comparing this value with computed F statistic values as shown in the ANOVA table, it is observed that the interaction effects AB, AC, BC and ABC are all significant. The main effects B and C are also having F statistic values greater than the table value of F statistics. However, since the interaction effects are significant, it is difficult to make any definite conclusions regarding the significance of the main effect. So that is the conclusions. Now, what you need to do in many a time, the full factorial experiment, 2 to the power k full factorial experiment may not be feasible. That means if say the number of factors is reasonably very high, and even if each factor is at 2 levels, you will find for each replication you need to conduct several sorts of conduct experiments at different a large number of treatment combinations. So this may not be feasible when you have limited time and limited resource. So you need to opt for the fractional factorial experiment. So many a time, due to cost and time consideration, it may not be possible or necessary to run all the experiments as required for a full factorial experiment. So in these conditions, we prefer using fractional factorial experiment. So for example, for a 2 to the power 6 factorial experiment, 64 experimental runs are required for a full replication, just one replication. So there are 6 main effects, 15 two-way interactions, 20 three-way interactions, 15 four-way interactions, 6 five-way interactions and 1 six-way interaction. So these are the possibilities, that there are 63 degrees of freedom, and if only the main effects and the two-way interactions, which require 21 degrees of freedom for estimation in total, are considered relevant in this experiment, it is better if a fractional factorial experiment is opted for. Is it okay? So this is the basis. So this is the basic purpose and objective of fractional replication of factorial experiment. Among the fractional factorial experiment, a half fraction of 2 to the power k experiment, denoted as 2 to the power k minus 1 factorial experiment, is a special case. Details of the experiment are given below. It is essentially the fractional factorial experiment you do, and what you try to do, that means all the treatment combinations you do not consider. So if it is a half fractional factorial, that means you just consider half of that means the total number of treatment combinations. So here you need to define the defining contrast I associated with the three-way interactions ABC, and hence I is ABC. For a 2 to the power 3 minus 1 fractional experiment, the treatment combinations associated with plus signs in the defining contrast are only selected. So from table 1, these are represented as A, B, C and ABC, which involve only 4 runs. So in the full factorial there are 8 runs. So now you just get 4 runs. That means only these 4 treatment combinations you consider. So 4 other treatments with minus signs in the defining contrast can also be selected. In this case, the treatment combinations are 1, AB, AC and BC. So the choice is yours. Either you go for say the principal fraction, or you may go for alternate fraction. So this is the alternate fraction and this is the principal fraction. These are the terms we use. So when you apply this 2 to the power 3 minus 1 say the fractional factorial experiment, that means half fractional factorial experiment, that means the main effect is defined by this main effect of A, main effect of B, main effect of C. So the lowercase letters represent the sum of responses in the corresponding treatments. So this is the lowercase letters. Okay, so this way you conduct. And however, in a fractional factorial experiment, these expressions, strictly speaking, represents a combined effect of the factor shown and its aliases. Similarly, the estimates for the 2 factor interactions that also conduct like this. That means here so AB, AC and BC. Against these expressions also represent the combined effect of the factor and its aliases. So I suggest that all the steps are given and for conducting fractional factorial experiment, and what is important thing is that the linear combination of the sum of the treatment responses that estimates the main effect A also estimates the interaction BC. Is it okay? So that you need to consider that A is equivalent to BC, the B is equivalent to AC, C is equivalent to AB. So okay, so and that's why A and BC are said to be aliases. Similarly, B and AC are said to be the aliases, and similarly the C and AB are considered to be the aliases. Okay, so this particular term we use, right? So this is an example. So please go through these examples. Consider 2 to the power 4 factorial experiment using BC as the defining contrast. Find the treatment combinations in a 2 to the power 4 minus 1 fractional factorial experiments. Find also the aliases of the contrast and estimate the effects of the contrast BC. So determine the treatment combinations in a 2 to the power 4 minus 2 fractional experiment. Is it okay? Fractional factorial experiment. If AD is taken as the defining constant, find also the aliases of the contrast. So these are the typical problems we set under fractional factorial experiment. You just all the steps I have written, please go through them, because the theory part already you have explained, and so you will find reasonings that of computing all these interaction effects as well as the main effects. And then what when you carry out all these exercises, you will come to know that why a fractional factorial experiment is preferred in many cases, and what is positive points and what are its limitations. So I think that we have identified all the important aspects related to the statistical design of experiments, and whenever you try to improve the quality level of a product or a process, many a time you need to look at the design, and when you try to propose a new design, you need to go for the design by experiments. Okay, so the design of experiments related the methodologies you have to use, and in many cases for product development purposes, keeping in mind the importance of quality features in the product or the quality performance, always we opt for design of experiment based say the approaches. Okay, so I conclude this particular session on quality by experimental design.